The cosmos holds secrets that defy our everyday logic. This journey reveals 25 surprising space facts that will fundamentally change how you see the universe. You will discover truths more astonishing than science fiction, from planets of diamond to the eerie music of empty space. How can a day last longer than a year? What mysterious force could be hiding a giant planet in our own solar system? The universe is a place of endless wonder, and we are just beginning to understand its rules. Are you ready to have your mind blown? That silent partner in our sky is not a permanent fixture. The moon is slowly, steadily drifting away from us. Each year, it retreats another 1.5 inches, roughly the length of a paperclip. This tiny annual shift might seem insignificant, but over the vast stretches of cosmic time, it reshapes the very nature of our world. The cause is a celestial tug of war. Earth's gravity pulls on the moon, but the moon's gravity also pulls on Earth, particularly on our planet's oceans. This creates the ocean tides, those massive bulges of water. Because Earth rotates faster than the moon orbits, our planet essentially drags this tidal bulge slightly ahead of the moon. That bulge, in turn, exerts its own gravitational pull, giving the moon a tiny, constant push forward in its orbit. This push transfers energy, slowly boosting the moon into a higher, more distant path. The consequence is a gradual, mutual slowdown. As the moon moves farther out, Earth's own rotation is slowing down. Billions of years from now, a day on Earth will no longer be 24 hours. It could stretch to be 25, then 30, as our planet's spin gradually matches the moon's orbit, and those breathtaking total solar eclipses where the moon perfectly covers the sun. They will become a relic of the past. In the distant future, the moon will appear too small in our sky to completely block the sun's disk, turning totality into a permanent historical event. This slow cosmic dance reminds us that even the most familiar celestial relationships are dynamic, written in the language of gravity and time. That gradual retreat of our moon is a masterclass in celestial patience, but other worlds in our solar system operate on a far more bizarre clock. Venus presents a reality so upside down that the very definitions of day and year lose their meaning. On this cloud-shrouded world, a single day, the time it takes for Venus to spin once on its axis, lasts 243 Earth days. Yet its journey around the Sun, an entire year, is completed in just 225 Earth days. This means a year on Venus is actually shorter than its day. To live there would be to experience a sunrise so rare it occurs only twice per Venusian year, with the sun rising in the west and setting in the east due to the planet's backward or retrograde rotation. This slow, reversed spin is one of the solar system's great mysteries. The leading theory points to a cataclysm in the deep past, a colossal impact, perhaps with a protoplanet early in the solar system's history, could have struck Venus with such force that it literally knocked the planet over, sending it spinning in the opposite direction and dramatically slowing its rotation. The aftermath of such a violent event still defines the planet's reality today, a world where time itself is turned inside out, reminding us that the calm order we see in the night sky can be the scarred aftermath of ancient chaos. Venus shows us time can be twisted, but the universe also holds the very essence of life in places we would least expect. Floating in the unimaginable depths of space, some 12 billion light-years from Earth, there is a cloud. It is not made of dust or gas, but of something profoundly familiar. This is a reservoir of water vapor, a cosmic ocean of such staggering scale it defies comprehension. It contains roughly 140 trillion times all the water in Earth's oceans combined. To put that into perspective, if you could gather every drop from every sea, every lake, every river and glacier on our planet, you would need 140 trillion copies of that to equal the water held in this single, distant cloud. It surrounds the heart of a voracious feeding frenzy, a supermassive black hole powering a brilliant object known as a quasar. The intense energy from this cosmic engine illuminates the vast cloud, allowing astronomers to detect its faint signature across the cosmic void. This discovery is not just about breaking records for size. Its true significance lies in its age. The light we see from this quasar left on its journey 12 billion years ago, when the universe itself was only about 1.6 billion years old. This tells us that water, that fundamental ingredient for life as we know it, was already abundant in the cosmos when it was still in its relative infancy. It means the building blocks for oceans and atmospheres were being manufactured on a galactic scale, long before our solar system even began to form. The universe, it seems, was preparing the stage for life long before there was a single star or planet to host it, scattering the seeds of future worlds in the luminous halos of ancient black holes. These cosmic oceans of water vapor exist on a scale we can barely fathom, but the universe is equally capable of compressing matter into forms of unimaginable intensity. Among the most extreme objects born from a star's death is the neutron star. Picture the core of a massive star many times heavier than our Sun, collapsing under its own gravity in a cataclysmic supernova explosion. What remains is not a quiet ember, but a city-sized sphere of pure, insane density. The force of that collapse is so profound that it crushes atoms themselves. Electrons are driven into protons, merging to form neutrons, until the entire star is essentially a giant atomic nucleus, a solid ball of nuclear material. The numbers defy belief. A single sugar cube of material from a neutron star brought to Earth would weigh about 1 billion tons. That is the mass of a small mountain, compressed into a volume you could hold between your fingers. To put it another way, if you could somehow take Mount Everest and crush all of its rock and ice down, you could fit it into a single teaspoon. This density creates gravity of monstrous strength. If you were to drop a marshmallow onto the surface of a neutron star from just 1 meter above, it would hit with the energy of 1,000 hydrogen bombs, its atoms instantly fused into the star's crust. Some neutron stars spin at dizzying speeds, completing hundreds of rotations every single second. As they spin, beams of radiation shoot from their magnetic poles like cosmic lighthouses. When these beams sweep across Earth, we detect them as precise, repeating pulses of light and radio waves, earning these objects the name pulsars. They are the universe's most accurate clocks and some of its most violent relics, proving that in the aftermath of stellar death, reality can become stranger than any fiction. The ferocious density of a neutron star shows how matter can be compressed, but in the vast atmosphere of Jupiter, a different kind of power has been on display for centuries. The Great Red Spot is a tempest of such monumental scale that our entire planet could fit inside it. This swirling crimson vortex is a hurricane that has raged for at least 350 years, possibly far longer, a permanent fixture in Jupiter's dynamic cloud bands. Yet, this ancient storm is not the eternal giant we once believed. For decades, astronomers have watched it steadily shrink. When the Voyager spacecraft flew by in the late 1970s, the storm was wide enough to hold 3 Earths side by side. Today, measurements from the Juno orbiter reveal it can barely contain one. The storm is not just getting narrower, it is also becoming more circular, as if the immense forces that sustain it are slowly losing their grip. The question of why this is happening is a complex puzzle. Some scientists suggest that smaller eddies and storms, constantly churning in Jupiter's atmosphere, are interacting with the Great Red Spot's outer winds, acting like brakes and gradually stealing its energy. Others propose that internal changes in the storm's dynamics, perhaps shifts in how it pulls heat from the planet's depths, are causing it to weaken. While it is unlikely to vanish overnight, the long-term trend points toward a solar system without one of its most iconic landmarks. We are witnessing in real time the slow death of a storm that has existed since before the invention of the telescope, a humbling reminder that even the most colossal features in our cosmic neighborhood are temporary actors on a stage of unimaginable time. Jupiter's fading storm reminds us of cosmic change, but the true scale of the universe lies in numbers so vast they become almost meaningless. One of the most humbling comparisons ever made is this: there are more stars in the observable universe than all the grains of sand on every beach and in every desert on Earth. Let us break down that staggering claim. First, consider the sand. Geologists estimate our planet holds roughly 7.5 quintillion grains of sand. That is a 7 followed by 18 zeros, an almost inconceivable number just for the tiny particles covering our shorelines and dunes. Now look up. Astronomers calculate the number of stars within the observable universe. The sphere of space from which light has had time to reach us is around 200 billion trillion. That is a 2 followed by 23 zeros. To give that a name, it is roughly 200 sextillion stars. When you place these two impossible figures side by side, the cosmic one is at least 10,000 times larger. For every single grain of sand you could hold in your hand, there are 10,000 suns scattered across the cosmos. To visualize this, picture holding one grain of sand. That represents our entire sun and its planetary family. Now try to imagine a beach, not just any beach, but one that stretches from the Earth to the Moon and is a meter deep in sand. The stars in our Milky Way galaxy alone would outnumber those grains, and our galaxy is just one of perhaps 2 trillion other galaxies, each a swirling island of billions or trillions of its own stellar grains. This comparison does more than just astonish. It reveals a profound truth about the nature of space itself. With so many stars, the universe feels overwhelmingly crowded by the numbers, yet it is almost perfectly empty. The average distance between stars in a galaxy is millions of times greater than their own size. The cosmos is a vast, dark void where these pinpricks of light are unimaginably isolated, making the existence of each star and each potential world orbiting it a rare and precious island in an endless, silent sea. That cosmic sea of stars may feel empty, but within our own solar neighborhood, a single object holds near total dominion. Our sun is not merely the brightest light in our sky, it is the overwhelming gravitational anchor of our entire system. In fact, 99.86% of all the mass in the solar system is contained within the sun itself. Every planet, from tiny Mercury to massive Jupiter, every moon, every asteroid tumbling in the belt, every distant comet in the Oort cloud, all of it combined amounts to a mere 0.14% of the total. To visualize this staggering imbalance, picture a giant pie chart. Almost the entire circle, a solid block of color, represents the sun. The sliver left for everything else is so thin you would struggle to see it. If you built a scale model where the sun was a bowling ball, all the planets together would amount to a few grains of pepper scattered around it. This sheer concentration of mass is the reason for the sun's absolute gravitational command. Its pull is what sculpts the orbits of every object, from the stately procession of the gas giants to the wild, elongated paths of comets. It dictates the rhythm of our years and the stability of our cosmic address. We often think of the solar system as a collection of diverse worlds, but in a very real sense, we are all just minor details, tiny bits of cosmic debris orbiting a single, magnificent star that holds almost everything there is. The sun's immense gravity may command our system, but it cannot project the most fundamental force of our world, sound. We often imagine the cosmos as a place of perfect, eternal silence, a vacuum where nothing can be heard. This is only half true. Sound as we know it, the vibration of molecules bumping into each other, cannot travel through the near-perfect emptiness between stars and planets. But to say space is silent is to ignore a symphony of a different kind. Space is filled with electromagnetic radiation, from radio waves to plasma vibrations, and with the right technology, we can translate this energy into sounds we can hear. Spacecraft like Voyager and Cassini have done exactly this, becoming our ears in the void. They have captured the haunting whispers of planets. The result is an eerie and powerful auditory experience. Saturn emits deep, rumbling roars from its immense magnetic field, a ghostly choir of charged particles. Jupiter's moon Io, the most volcanically active world in the solar system, creates a constant crackle of radio noise as it interacts with Jupiter's magnetosphere, sounding like a celestial fire crackling across 500 million miles. Even the echo of creation itself has a voice. The cosmic microwave background, the afterglow of the Big Bang, can be converted into a deep, resonant hum, the fundamental bass note of the universe. Perhaps most striking are the pulsars, those rapidly spinning neutron stars. Their beams of radiation, converted into sound, produce a precise, rhythmic ticking, like a metronome keeping perfect time for millions of years. Listening to these sounds transforms our understanding. The cosmos is not a silent movie. It is a grand opera broadcast on a frequency we were born unable to hear, a reminder that reality extends far beyond the limits of our own senses. The haunting sounds of space reveal a dynamic universe, but even the silent, solid worlds are hiding dramatic changes. Mercury, the sun-scorched innermost planet, is in fact getting smaller. For decades, astronomers theorized this might be happening, but it was the Messenger spacecraft that delivered the definitive proof. The planet is literally wrinkling like a dried-out grape. The cause lies deep within its structure. Mercury has an enormous iron core, proportionally larger than that of any other planet in our solar system. This core has been slowly cooling down over billions of years. As it cools, the metal contracts, pulling the entire planet inward, but the rocky outer crust cannot simply shrink smoothly like a deflating balloon. It is brittle, so instead of compressing evenly, it fractures and breaks. Huge sections of crust are thrust upward and over other sections, creating towering cliff faces called lobate scarps. These are not like mountains pushed up from below. They are wrinkles of compression, evidence of the planet's skin tightening. Some of these scarps are hundreds of miles long and rise over a mile high, making them some of the most dramatic geological features in the solar system. The Messenger images show them crisscrossing the ancient cratered surface, sometimes even cutting right through old impact basins. This tells a powerful story. Because these scarps deform craters that are billions of years old, we know the shrinking process has been ongoing for most of Mercury's history. It is a world that has been slowly cinching its belt for eons, a gradual transformation driven by the silent, relentless cooling of its heart. This makes Mercury far more than a static, airless rock. It is a planet with a long and active geological life, its surface a testament to the powerful forces hiding within seemingly dead worlds. Mercury's slow contraction reveals a hidden inner life, yet the outer fringes of our solar system may conceal an even greater secret, a ghost world whose gravity we can feel but cannot see. Astronomers have gathered compelling, though still unconfirmed, evidence for the existence of a ninth planet, a hypothetical giant lurking in the perpetual twilight beyond Neptune. The clues are not a direct sighting, but a strange pattern written in the paths of tiny, icy objects. Far out in the Kuiper belt, a vast disk of frozen leftovers from the solar system's formation, there are several dwarf planets and smaller bodies with orbits that are not randomly scattered. Instead, their elongated paths are mysteriously clustered, as if something massive is herding them, tugging their trajectories into alignment over millions of years. The gravitational influence required to create this pattern points to an unseen shepherd, a planet with a mass roughly 5 to 10 times that of Earth. This would make it a super-Earth or a mini-Neptune, a type of world common around other stars but missing from our own cosmic family portrait. Its orbit, if it exists, would be a colossal ellipse, tilted at an angle compared to the rest of the solar system. At its closest approach, it might swing within a few hundred astronomical units of the Sun, still vastly farther out than Neptune. At its most distant, it could retreat over 1,000 astronomical units into the deep freeze, taking perhaps 10,000 to 20,000 Earth years to complete a single, lonely journey around our star. Animated simulations of this potential path show a dark, cold world tracing a slow, majestic arc through the blackness, its gravity subtly orchestrating the dance of smaller objects from an unimaginable distance. Finding this phantom planet is one of astronomy's greatest modern quests, a cosmic detective story where the clues are gravitational whispers in the dark. It is a reminder that our map of the solar system, which seems so complete, may still have a giant blank space waiting to be filled. The search for hidden giants reveals a solar system still full of surprises, but the true diversity of worlds extends far beyond our own star. Among the thousands of planets discovered orbiting other suns, one stands out for its almost unimaginable composition. Designated 55 Cancri. This world is a super-Earth, a rocky planet about twice our size and 8 times our mass, orbiting perilously close to its host star. Its year lasts a mere 18 hours, and surface temperatures soar to thousands of degrees, hot enough to melt most metals. But the true wonder lies beneath that infernal surface. Astronomers, using spectroscopic observations from telescopes like Spitzer and Hubble, have analyzed the light filtering through the planet's thin atmosphere during its transits. The chemical signature they detected pointed overwhelmingly to carbon, not the oxygen and silicon that make up the bulk of Earth's rocks. This suggests a world with a radically different origin story. 55 Cancri likely formed in a part of its protoplanetary disk that was carbon-rich, like a cosmic soot belt. Given its immense mass and the crushing pressures inside, scientists believe much of that carbon has been compressed into crystalline structures. In other words, a significant portion of this planet could be one colossal diamond. Picture a world where the very ground beneath your feet, if you could stand on its molten surface, might be a crust of graphite giving way to a mantle hundreds of miles thick of solidified diamond. This is not a gemstone you could mine, but a fundamental geological layer as common there as granite is here. The existence of such a world shatters our Earth-centric view of what a planet can be. It tells us that the ingredients available during a star system's birth can forge worlds of staggering exoticism, from graphite spheres to diamond fortresses, expanding the catalogue of possible planets into realms once confined to fantasy. The possibility of diamond worlds expands our vision of what a planet can be, yet the universe itself holds a deeper and more unsettling mystery about its own fundamental nature. For over a century, we have known the cosmos is expanding, with galaxies flying apart from one another. The rate of this expansion is governed by a single, crucial number called the Hubble constant. Pinpointing this number is the key to understanding the universe's age, its size, and its ultimate fate. But today, a troubling discrepancy has split cosmology in two. It is known as the Hubble tension, and it is arguably the most significant unsolved problem in modern astronomy. On one side, we have meticulous measurements of the early universe, primarily from the cosmic microwave background radiation, the faint afterglow of the Big Bang. The Planck satellite mapped this ancient light in exquisite detail, and from its patterns, scientists can calculate what the expansion rate should be today, following the well-tested laws of physics. This gives us one very precise value for the Hubble constant. On the other side, astronomers use a cosmic distance ladder, observing pulsating stars called Cepheids and brilliant stellar explosions known as Type 1, a supernova in relatively nearby galaxies. These are our standard candles, objects of known intrinsic brightness that allow us to measure cosmic distances directly. When we measure how fast these galaxies are moving away, we get a direct modern measurement of the expansion rate. The problem is stark. The two numbers do not agree. The local universe, measured with stars and supernova, appears to be expanding significantly faster than the pristine early universe data predicts. This is not a small margin of error. It is a persistent gap that has survived over a decade of increasingly precise observations. It means one of our most cherished assumptions about the cosmos might be subtly wrong. The implications are profound. This tension could be pointing to something missing from our cosmic recipe book. Perhaps dark energy, the mysterious force accelerating the expansion, is not constant but has evolved in strength over time. Maybe there is a new, unknown type of neutrino or another exotic particle from the early universe subtly altering the expansion history. Or, most excitingly, it could indicate a flaw in our understanding of gravity itself, a hint that Einstein's theory of general relativity, while spectacularly successful, needs modification on the largest scales. The Hubble tension is more than a technical disagreement. It is the universe whispering that we have overlooked a crucial piece of the puzzle, a hidden ingredient or a new rule that could rewrite the story of everything. While the Hubble tension hints at flaws in our cosmic understanding, the solar system still holds monuments that dwarf anything on Earth. Mars is home to a geological titan, Olympus Mons, the largest volcano in the solar system. This is not merely a mountain, it is a landscape in itself, a shield volcano so vast its base would cover the entire state of Arizona. To grasp its scale, picture Mount Everest, the tallest peak on our planet. Now stack two more Everests on top of it. Olympus Mons would still tower over that pile, standing nearly 22 kilometers or about 13.6 miles high from its base. But its true wonder is not just its height, it is its breadth. The volcano's slopes are so gentle that if you stood on its rim, the summit would be hidden beyond the horizon. You would be standing on a slope that feels almost flat, yet you are already on a mountain taller than any on Earth. The reason for its monstrous size lies in a fundamental difference between Mars and our own world. On Earth, our crust is broken into tectonic plates that slowly drift over the hot mantle below. As a volcanic hotspot pushes magma upward, it can create a chain of islands like Hawaii as the plate moves over it. Mars, however, has a single, stationary crust. For billions of years, a single plume of hot magma could keep pushing up through the same spot on the Martian surface, layer upon layer of lava flow after lava flow, with nothing to move the volcano away from its source. Olympus Mons did not erupt with violent explosions, but with countless slow, oozing flows that built its immense, gentle profile over eons. Orbital images from spacecraft like Mars Express and the Mars Reconnaissance Orbiter reveal a breathtaking panorama. Its caldera, the summit crater, is a complex of collapsed pits over 50 miles wide, large enough to swallow entire cities. The cliff encircling its base is a sheer wall several miles high, a final testament to the lava flows that once met the ancient plains. This is a fossil of planetary geology, a record of a time when Mars was a world of fire, its internal heat pouring out to construct a peak that will likely never be rivaled in our solar system. Olympus Mons stands as a monument to a fiery past, but another iconic feature of our solar system is far more fleeting than its grandeur suggests. Saturn's magnificent rings, those breathtaking bands of ice and dust, are not a permanent part of the planet. They are a recent and temporary spectacle. For a long time, astronomers assumed the rings were as old as Saturn itself, around 4.5 billion years. But data from the Cassini spacecraft's final, daring orbits painted a radically different picture. By precisely measuring the gravitational pull of the rings and analyzing how they filtered charged particles, scientists made a startling calculation. The rings are remarkably clean and bright, not darkened by eons of accumulated cosmic dust. Their total mass is also much lower than expected for ancient structures. The evidence points to a youthful age of only about 100 to 200 million years. This means when dinosaurs ruled the Earth, Saturn likely did not wear its famous crown. Their origin story is one of celestial violence. The most compelling theory suggests a former icy moon, perhaps one as large as Saturn's current moon Mimas, strayed too close to the planet. Saturn's immense tidal forces would have torn this moon apart, grinding its ice into countless fragments that were then shepherded by the gravity of Saturn's other moons into the dazzling, flat disk we see today. This beautiful structure is not only young, it is actively vanishing. Cassini also confirmed the existence of ring rain. Micrometeoroid impacts and sunlight electrically charge tiny ice particles in the rings, allowing Saturn's magnetic field to pull them down into the planet's upper atmosphere. This process is a constant, gentle shower of ring material, draining away the equivalent of an Olympic-sized swimming pool of water every half hour. At this rate, the rings may have only another 100 million years left before they fade from view, a mere blink in cosmic time. We are living in a privileged era, able to witness one of the solar system's most stunning decorations during its brief, brilliant prime. Saturn's rings are a fleeting masterpiece of cosmic destruction, but the quest for ultimate cold reveals a universe where temperature itself can be turned into a tool for discovery. The coldest natural place we have ever found is not in the dark void between galaxies, but closer to home, in the beautiful death throes of a star. The Boomerang Nebula, a pre-planetary nebula about 5,000 light-years away, is a cosmic refrigerator. As an aging star sheds its outer layers in a fast, expanding wind, the gas cools dramatically through a process similar to how a refrigerator works. This expansion causes the molecules to lose energy, dropping the temperature to just 1 degree above absolute zero, a mere 1 Kelvin. That is minus 457.87 degrees Fahrenheit. At this temperature, molecular motion nearly stops, making it the coldest known natural spot in the entire universe. Yet here on Earth, inside unassuming laboratories, we have created temperatures that make even the Boomerang Nebula seem warm. Using a remarkable technique called laser cooling, scientists can slow atoms down to a virtual standstill. They do this by firing precisely tuned lasers at a cloud of atoms, like photons of light acting as tiny brakes. Each time an atom absorbs a photon moving in the opposite direction, its momentum decreases and it slows down. Since temperature is fundamentally a measure of how fast particles are moving, slowing the atoms cools them down. Through this method, physicists have achieved temperatures just a few billionths of a degree above absolute zero. That is over 1 billion times colder than the depths of the Boomerang Nebula. At these almost unreal temperatures, matter begins to behave in ways that defy our everyday experience. Atoms lose their individual identities and merge into a single, coherent quantum wave, a state known as a Bose-Einstein condensate. In this exotic form of matter, thousands or millions of atoms act as one superatom, exhibiting bizarre properties like superfluidity, where they can flow without any friction, even climbing up the walls of their container. This is not just a laboratory curiosity, it is a window into the quantum world, allowing us to probe the fundamental rules that govern reality at the smallest scales. It is a profound thought that the most extreme cold in the cosmos is not found in the infinite dark, but right here, created by human ingenuity to unveil the universe's deepest secrets. Our ability to create such extreme cold reveals the strange frontiers of physics, but the universe is equally capable of forging worlds that are the very definition of hellish fire. Among the catalogue of exoplanets, one stands out for a storm of almost artistic cruelty. HD 189,733b, a gas giant about 63 light-years away, is a world where the sky rains molten glass. This cobalt blue jewel in the cosmos hides a furnace of unimaginable violence. The planet is locked in an achingly tight orbit around its orange dwarf star, completing a year in just 2.2 Earth days. This proximity creates a gravitational embrace so powerful that the planet is tidally locked, forever presenting the same scorching face to its sun while the far side languishes in eternal night. The temperature difference between these two hemispheres is catastrophic, driving winds that do not merely howl. They scream across the planet at speeds exceeding 5,000 miles per hour. These are supersonic gales moving several times faster than a bullet that blast around the planet in a permanent, superheated hurricane. The atmosphere itself is a swirling cauldron of vaporized rock. Temperatures on the dayside soar to around 1,700 degrees Celsius, hot enough to melt iron and vaporize silicates, the minerals that make up glass and sand on Earth. Scientists believe that within the upper layers of this seething atmosphere, tiny particles of silicate condense as clouds. But these are not clouds of water, they are clouds of molten rock. As these droplets grow heavier, they begin to fall. What follows is a rain of liquid glass propelled sideways by those 1,000-mile-per-hour winds. Picture a storm where the raindrops are blazing, molten shards, flying horizontally in a blue-hazed sky, scouring the landscape in a relentless, fiery sandblast. The planet's beautiful azure color, likely caused by the scattering of light through these silicate particles, is a cosmic irony, the mark of a beautiful, burning tomb. This is a world where the very sky is a weapon, a reminder that the universe crafts not just diamonds but nightmares of stunning, lethal elegance. The universe's most beautiful horrors are matched by its most profound mysteries, and for decades, cosmologists faced a glaring inventory problem. All the ordinary matter, the atoms that make up stars, planets, and us, seemed to be only half accounted for. We could tally the mass in galaxies and galaxy clusters, but it fell far short of the total predicted by our models of the Big Bang and cosmic evolution. This was the case of the missing baryons, a cosmic whodunit where the suspect was nearly half of all normal matter in the universe. Where could it have gone? The answer was hiding in plain sight, woven into the very fabric of the cosmos. Theorists long suspected this missing matter existed as a diffuse, superheated gas spread through the vast filaments of the cosmic web. This is the grand architecture of the universe, a network of dark matter scaffolding along which galaxies are strung like pearls on a string. The spaces between these great walls and filaments were thought to contain a thin, searing plasma, a gas so hot it emits only faint, high-energy X-rays and is too wispy to see directly with telescopes. Proving it was there required a brilliant new tool, a cosmic flashlight beamed from the other side of existence. That tool is the fast radio burst, an intense millisecond flash of radio waves from distant galaxies. As these powerful bursts travel billions of light years to reach us, they pass through all the material between their source and Earth. Each atom, each electron in that material slows the burst's radio waves by a tiny, measurable amount. By analyzing the precise delay in the burst signal, astronomers can essentially weigh all the stuff it passed through. When researchers studied a series of these bursts, they found the telltale signature of that long-sought material. The missing baryons were not in some hidden dimension or locked inside black holes. They were right there, filling the cosmic arteries between the galaxies. This intergalactic medium is a ghostly ocean of million-degree plasma, a reservoir containing enough atoms to finally balance the universe's books. It is a humbling discovery, reminding us that most of the ordinary universe is not in the brilliant islands of stars, but in the dark, hot sea that connects them all, a fundamental part of reality we have only just learned to see. Our planet's portrait from space presents a serene blue marble, a perfect sphere floating in the void. Yet this image is a beautiful illusion. Earth is not a perfect sphere at all, but an oblate spheroid, gently squashed at the poles and bulging at its waistline. This equatorial bulge is a direct gift of our planet's rapid spin. As Earth rotates, the centrifugal force pushes material outward, much like how a pizza chef stretches dough by spinning it. This force is strongest at the equator, where the rotational speed is greatest, causing our world to swell. The numbers make this abstract idea concrete. Earth's diameter measured from pole to pole is about 7,909.75 miles, but its diameter across the equator is roughly 7,926.27 miles. That is a difference of over 16.5 miles. To visualize this, if you shrank Earth down to the size of a standard classroom globe, that bulge would be less than the thickness of the vinyl coating, completely invisible to your eye. The shape is so subtle that from space it appears perfectly round, a testament to the vast scale of our world. But the story of Earth's shape grows even more fascinating when we move beyond this simple bulge. The true, most accurate model of our planet is not a spheroid, but something called the geoid. Imagine Earth completely covered by a global ocean, unaffected by winds or tides, shaped only by the planet's gravity and rotation. The surface of that imaginary ocean is the geoid. It represents where gravity is perfectly equal, a surface that is always perpendicular to the downward pull. This is not a smooth mathematical shape, because Earth's interior is not uniform with varying densities in the mantle and crust. The gravitational pull is slightly stronger in some places and weaker in others. These variations sculpt the geoid into a lumpy, potato-like form. There are massive gravitational highs like a swell south of India and profound lows. One of the most dramatic features is the Indian Ocean geoid low, a vast depression in the gravity field just south of Sri Lanka. Here, the sea level, if measured by the geoid, is over 300 feet lower than the global average. This does not mean there is a giant hole in the ocean. Water naturally flows to fill it, but it means the very definition of level is warped by the planet's hidden interior. Exaggerated models of the geoid reveal a world that looks bizarrely misshapen, with bulges and dimples that tell a hidden story of ancient tectonic slabs sinking into the mantle and plumes of hot rock rising from the core. Our home is not a simple sphere, but a dynamic, gravitationally sculpted world, its truest shape written in the silent, invisible language of its own internal mass. Our own planet's hidden shape is shaped by deep forces, but our silent companion in the sky also has a hidden, trembling life. The moon is not a dead, static world. It experiences its own version of earthquakes known as moonquakes. For years after the Apollo astronauts left, the instruments they placed on the lunar surface continued to listen, revealing a surprisingly active seismic world. The data from those Apollo seismometers painted a complex picture, identifying 4 distinct types of lunar tremors. The deepest moonquakes originate roughly 700 kilometers below the surface, triggered by the relentless gravitational tug of Earth. As our planet pulls on the moon, it stresses the lunar interior, causing deep fractures to slip and grind. Then there are the shallow moonquakes, which are far more powerful and mysterious. These can register up to 5.5 on the Richter scale and last for astonishingly long periods, sometimes over 10 minutes. On Earth, quakes typically last for seconds, maybe a minute, because our planet's water and fractured crust dampen the vibrations. The moon, being dry and rigid, rings like a giant, solid bell, allowing seismic waves to echo and reverberate for what feels like an eternity. The third type are thermal moonquakes. After 2 weeks of deep freeze lunar night, the surface temperature plummets to around -173 degrees Celsius. When the sun finally rises, the crust heats up rapidly by over 250 degrees, and this extreme thermal expansion causes the brittle rock to crack and pop with predictable regularity every lunar morning. Finally, there are the quakes caused by meteoroid impacts as space rocks of all sizes constantly bombard the surface. Understanding these tremors is not just academic, it is a matter of survival for the future. If we are to build permanent lunar bases, we need to know if the ground itself is stable. A powerful, long-lasting shallow moonquake could devastate structures not designed for such prolonged shaking. By mapping the moon's seismic hotspots and understanding its internal rumbles, we can choose safer locations and engineer habitats that can withstand the unique vibrational fury of our closest celestial neighbor. The moon's hidden tremors remind us that even seemingly dead worlds have an inner life. Yet the very definition of a star is being rewritten by discoveries in our own cosmic backyard. We think of stars as unimaginably hot furnaces, and for the most part that is true. Our sun's surface simmers at around 5,500 degrees Celsius. But at the faint, cool edge of stellar classification exists a family of cosmic failures known as brown dwarfs. These are objects that formed like stars from collapsing clouds of gas, but they simply did not gather enough mass to ignite the sustained nuclear fusion of hydrogen in their cores, the process that makes a true star shine. They are the in-between worlds, too massive to be planets but too feeble to be full-fledged stars. For decades, they were theoretical ghosts, but we now know they are incredibly common. And among them, the coolest class of all are the white dwarfs. These are the most star-like objects in temperature you could ever hope to encounter. Astronomers using NASA's WISE space telescope have identified white dwarfs with atmospheric temperatures chillingly close to that of our own planet. The current record holder, WISE 0855-0714, is estimated to have a surface temperature somewhere between -48 and -13 degrees Celsius. That is colder than a winter day in Siberia and could be as mild as a cool afternoon on Earth. To put it in perspective, you could theoretically stand in the upper atmosphere of such an object and feel a temperature not unlike a breezy summer day. Now, of course, you could not literally reach out and touch it. The surface gravity on even a small brown dwarf would be crushing, dozens of times stronger than Earth's. And its atmosphere would likely be a toxic, turbulent mix of hydrogen, helium, and exotic compounds like ammonia and water vapor clouds. But the sheer fact that such an object exists, glowing with the faint, leftover heat of its formation rather than the fire of fusion, shatters our celestial categories. It means the line between the warmest planets and the coolest stars is not a bright line at all, but a blurred and fascinating frontier where failed stars smolder in the dark, holding temperatures we can finally comprehend on a human scale. That blurred frontier between stars and planets exists within a galaxy we think of as stable, but even our cosmic home is not an island destined for solitude. The Milky Way is on an inescapable collision course. Our grand spiral galaxy and its nearest large neighbor, the Andromeda Galaxy, are caught in a mutual gravitational embrace, pulling them toward a future merger. Right now, Andromeda is racing toward us at about 250,000 miles per hour. But do not panic, the timescale here is almost beyond human comprehension. The actual impact, the moment when the two galaxies begin to intertwine, is still about 4.5 billion years away. By that time, our sun will have already swelled into a red giant, fundamentally altering our solar system long before the galactic fireworks begin. So what would this epic event look like from a hypothetical future Earth? At first, over billions of years, Andromeda would grow from a faint smudge in the constellation, bearing its name into an impossible, brilliant spindle stretching across the night sky. As the galaxies drew closer, their mutual gravity would begin to warp their majestic spiral arms, pulling out immense streams of stars, gas, and dust in long, luminous tidal tails. The sky would become a canvas of cosmic chaos and beauty, filled with countless new stars as the collision compressed vast clouds of gas, triggering furious waves of stellar birth. The core of Andromeda would blaze as a second, brilliant hub of light. Crucially, despite the spectacle, direct collisions between stars are extraordinarily unlikely. Galaxies are mostly empty space. The average distance between stars is so vast that even when two galaxies pass through each other, their stars will simply slide past one another like ghostly ships in the night. The real violence is reserved for the gas and dust between the stars, which will slam together, heat up, and glow with intense radiation. Over the next 1 to 2 billion years after the first close pass, the two galaxies will swing apart, then fall back together again, dancing in a series of ever-tightening loops until they finally settle. The end result will not be a spiral galaxy. The graceful pinwheels will be gone, stirred into a new, more amorphous shape. The merger will forge a single, giant elliptical galaxy, which astronomers have already nicknamed Milcomda. This future galaxy will be a vast, golden-hued sphere of older stars, with most of its gas used up in that final burst of star formation. Simulations of this event, based on precise measurements from the Hubble Space Telescope, show a breathtaking ballet of gravity. They depict two luminous disks stretching, merging, and finally relaxing into a smooth, egg-shaped glow. Our solar system will likely be flung into a much more distant orbit within this new galactic empire, but it will almost certainly survive the journey. This fate is not unique. It is the standard future for galaxies in a crowded universe. We live in a dynamic cosmos where even the grandest structures are temporary, destined to merge and transform on timescales that humble our brief existence. The grand merger of galaxies will sculpt the future universe, but today's cosmos is already a tapestry woven with threads of light and vast expanses of nothing. Between the great walls and filaments of the cosmic web lie the voids, the universe's empty rooms. The most famous of these is the Boötes void, a spherical chasm of staggering scale. It is not a perfect vacuum, but its emptiness is profound. Stretching an incredible 250 million light-years across, this region contains only a few dozen galaxies where scientists would expect to find thousands. If our Milky Way sat at its center, our nearest galactic neighbor would be tens of millions of light-years away, and the night sky would be almost devoid of other galaxies. To grasp this scale, imagine a sphere so vast that light, traveling at 671 million miles per hour, would take 250 million years just to cross from one side to the other. Within that incomprehensible volume, the galaxies are lonely, scattered islands. Three-dimensional maps of the observable universe reveal the Boötes void as a shocking, near-empty bubble nestled within the frothy structure of everything. How does such a colossal nothingness form? The answer lies in the very earliest moments after the Big Bang. Tiny quantum fluctuations in the primordial soup of the universe were stretched to enormous sizes by a brief period of hyper-expansion called inflation. These ripples in density became the seeds for all future structure. Where the initial density was slightly higher, gravity pulled more and more matter in over billions of years, forming the great galaxy clusters and filaments. Conversely, regions that started with slightly less material were left behind as matter drained away into the denser surroundings. The Boötes void is one of these underdense regions that grew to an extreme size, a fossil imprint of the universe's faintest first whispers. Its existence is not a flaw, but a fundamental feature of cosmic architecture, proving that emptiness is as much a part of the design as the glittering cities of stars. Even the most carefully planned journeys can hold hidden surprises, as the twin pioneers of deep space discovered. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were humanity's first emissaries to the outer planets and beyond. Their missions were triumphs, returning the first close-up images of Jupiter and Saturn before continuing on a one-way trip into the interstellar void. Yet as they drifted farther from the Sun, tracking their faint radio signals revealed a persistent and perplexing anomaly. Both spacecraft were experiencing a tiny, unexplained deceleration, a constant pullback toward the Sun that was about 10 billion times weaker than the gravity we feel on Earth. This minuscule force, just a fraction of what our models predicted, became known as the Pioneer anomaly. For decades, it haunted the edges of physics. Could it be evidence of a flaw in Einstein's theory of gravity? Was it the gravitational tug of unseen dark matter in our solar system, or perhaps even the hint of another, more exotic physical force? The mystery captivated scientists and fueled speculation, a ghost in the machine of celestial mechanics. Solving it required a monumental act of cosmic detective work. Teams of researchers spent years recovering and analyzing decades-old telemetry data, reconstructing the thermal and dynamical history of the two distant probes. They built incredibly detailed computer models of the spacecraft, accounting for every known force, from the gentle pressure of sunlight to the faint emission of heat from the spacecraft's own components. The breakthrough came from looking not outward into the cosmos, but inward at the spacecraft's design. The Pioneers were powered by radioactive thermoelectric generators, which produced heat that was radiated away into space. The key insight was that this heat radiation was not perfectly uniform. More heat was emitted from the rear of the spacecraft, where the power units were located, than from the front. This anisotropic or directionally uneven thermal radiation acted like a tiny, constant photon rocket. Each infrared photon carrying heat away from the craft also carried a minuscule amount of momentum. Because more photons were pushing off the back, the net effect was a tiny but steady push back toward the Sun, exactly mimicking an unexplained deceleration. It was a triumph of meticulous analysis over mystery. The Pioneer anomaly was not a gateway to new physics, but a lesson in humility and precision. It proved that even our most sophisticated instruments are part of the experiment, and that the universe often hides its simplest truths in the details we overlook. The ghostly deceleration of the Pioneer probes was solved by human ingenuity, but one signal from the void has stubbornly resisted all explanation. On the evening of August 15, 1977, the Big Ear radio telescope at Ohio State University was silently sweeping the sky, listening for whispers of cosmic origin. A computer printout from that night shows a simple column of alphanumeric codes, a log of signal intensity over time. And there, rising from the background noise, is a sequence, 6 characters, EQJ5. It represents a radio burst 72 seconds long, perfectly matching the telescope's field of view, so intense that it maxed out the equipment. The signal was narrowband, focused on the hydrogen line frequency, exactly the type of beacon a technologically advanced civilization might use to announce its presence. When astronomer Jerry Amon reviewed the data days later, he was so stunned by its perfect characteristics that he circled the alphanumeric sequence on the printout and wrote a single, emphatic word in the margin: "Wow." That exclamation gave the signal its immortal name. The WOW signal came from the direction of the constellation Sagittarius, and it has never been heard again. Decades of follow-up observations by more powerful telescopes, including the SETI Institute's Allen Telescope Array, have scanned that same patch of sky, listening intently. Only silence has answered. The lack of a repeat is the central mystery. If it was a deliberate broadcast from a distant star, why only once? The leading natural explanations are compelling but unsatisfying. Could it have been a reflection of a human transmission, perhaps from a secret military satellite, bouncing off a piece of space debris? The precise frequency and the telescope's specific characteristics make that extraordinarily unlikely. Some have suggested it was a comet, but the known comets in that region at that time did not match up. The signal remains a perfect enigma, a 72-second shout into the cosmic night that we happen to be listening in exactly the right place at exactly the right moment to hear. It stands as a tantalizing, singular event, a reminder that in the vast quiet of the universe, even one unexplained whisper can echo forever, daring us to keep listening. That singular, unexplained wow signal reminds us we are listening for cosmic company. But the deepest connection we have to the universe is not one we must hear, it is the very substance of our bodies. The final, most profound fact is this: every one of us is made of stardust. This is not a metaphor, but a literal chemical truth. Every atom of carbon in our cells, every molecule of oxygen we breathe, every particle of iron in our blood was forged in the heart of a star that lived and died long before our sun was born. The story begins with the Big Bang, which produced only the lightest elements, hydrogen and helium, with traces of lithium. For hundreds of millions of years, the universe was a vast, dark expanse of these simple gases. Then the first stars ignited, and within their searing cores, a miracle of cosmic alchemy began. Under unimaginable pressure and heat, hydrogen atoms fused into helium. As stars aged and their cores grew hotter, helium fused into carbon, and carbon into heavier elements like oxygen, neon, and silicon. This process is called stellar nucleosynthesis. For elements all the way up to iron, this fusion releases energy, powering the star's brilliant light. But iron is a dead end. Fusing iron consumes energy instead of releasing it. In a massive star, this iron core grows until it can no longer support its own weight, leading to a catastrophic collapse and a supernova explosion. That final, violent detonation is the universe's ultimate forge. The incredible energy of a supernova creates conditions hot enough and dense enough to slam atoms together, forging every element heavier than iron, from the gold in a wedding ring to the iodine in your thyroid. The explosion then blasts this newly minted material, this enriched stardust, across light years, scattering it into interstellar clouds. Our own solar system formed from just such a cloud, a cosmic recycling bin containing the ashes of countless ancient stars. The iron in the Earth's core, the calcium in your bones, the phosphorus in your DNA, all of it is second-hand stardust, assembled by gravity and time into planets and eventually into life. When you look up at the night sky, you are not just an observer, you are the universe looking back at itself. The carbon in your hand once fueled the nuclear fire of a giant star. The oxygen in your lungs was breathed out by a supernova. We are not merely in the cosmos, we are the cosmos, a temporary, conscious arrangement of atoms that once danced in the light of distant suns. From diamond worlds to phantom planets, we have traveled a universe of impossible extremes. These 25 glimpses are not just trivia, they are windows into a reality far more wondrous and bizarre than our everyday experience suggests. They reveal a cosmos where the rules are rewritten on a galactic scale, where time bends, matter transforms, and silence itself is an illusion. This journey underscores the profound mysteries still waiting in the dark, the staggering scales that humble our existence, and the beautiful, undeniable truth that we are woven from the fabric of the stars. The universe is not a distant spectacle, it is our origin story and our home. So, which fact reshaped your view of the cosmos? Share your favorite mind-blowing discovery in the comments below. If you enjoyed this voyage through the strange and spectacular, be sure to subscribe for more journeys to the edges of understanding. And tonight, when you step outside, take a moment to look up. Remember, you are not just looking at the stars, you are looking at where you came from and wondering with the rest of us what astonishing secrets remain to be found.